SwayamPrabha. Digital India. Educated India.
Okay, so let us continue the discussion on axial flow compressor, and what we are in the middle of the discussion is that we have started looking at the stage dynamics and how you need to design the axial flow compressor and rather the need of the axial flow compressor in the modern gas turbine engine, and then how the things actually changes the flow passages when it passes through rotor and stator. So, we will continue the discussion where we stopped in the last lecture, that during starting the first stage and the last stage design condition. So, this is what we looked at the first stage, and and we said this dark line will represent the starting and the dotted line will represent the design condition. And first stage, so this is how your velocity triangle would look like, and then these would be the conditions for design purposes. Now, at the second stage or rather last stage, the triangle would look like slightly different. So, this will go like this, and so you can see how it actually looks like, and this is U. So, this is W2, this would be W1, and as usual this is alpha 1, this is beta 1, alpha 2, beta 2, and this is my V1, and this would be V2, and the design condition may be like this, and the other case it would be like this. So, now this case, so this is the case where it is last stage velocity triangle. So, what happens if you look at it, that beta 1 greater than beta 1 design, alpha 1 would be greater than alpha 1 design, and beta 2 greater than beta 2 design, and alpha 2 greater than alpha 2 design. So, essentially alpha 1 and beta 2 are kept constant. So, which means alpha 2 and beta 1 actually increases. So, now the increase in alpha 2 and beta 1 or alpha 1 beta 2, so essentially increase the loading. So, whatever it happens, this happens. So, higher pressure rise plus and possible positive incident separation may cause stall and surge. Now, for last stages, our Vz is higher than the Vz design. So, when alpha 2 and beta 1 decreases, it actually at the same time decreases the loading on blade passages. So, this could be alpha 2 beta 1 or alpha 1 beta 2, alpha 1 and beta 2. So, either of them actually decreases, it decreases the loading. So, which means there is a negative incidence separation. Now, what happens during starting, front and back stages behave in opposite manner. So, this is what actually happened during starting. So, one can see that like for that's what for turbofans, what you can do, since the front stage and the back stage they behave in a different manner or rather opposite manner, you have a variation of blade speed can help to prevent failure, to maintain that ratio of Vz by u, which is sort of constant. So, what happens as Vz decreases, u decreases, which means rotational speed decreases, and as Vz increases, u increases, which means rotational speed also increases. So, just to accommodate this, one has to use multiple turbines. So, just to avoid the situation, or second situation could be blow up, which means take or rather bleed up, take some air at middle stages and pass it through the bypass. Thus, so when you do that, so you reduce m dot and hence Vz for later stages. Okay. So, this is what typically done in turbofan. So, these are the some of the issues. Now, another possibility during starting is that you can change the stator blade angles, which will provide a beneficial variation in alpha 1. So, that causes the right change in Vz. Or fourth, it could be you could design front stages for lower loading and back stages for higher loading. So, you can distribute the loading pattern. So, the front stages you design such that it actually the loading is low and the back stages could be the loading could be high, and that is the way if you design, probably you would be able to get a desired pressure rise without having too much of difficulties. Now, this you can think about from a design point of view. So, that in actual operation they may operate with similar characteristics, and this can prevent stall. So, that is one of the important situation what one would be. So, one can write like the pressure rise between P naught 3 by P naught 1 would be 1 plus eta st u square Cp T naught 1 delta V theta by u gamma by gamma minus 1, which is 1 plus eta st gamma root gamma r T naught 1 square delta V theta by u gamma minus 1. So, here this quantity, that u by gamma r T naught 1 is blade speed Mach number. So, this is another important parameter while looking at the design. Now, when you talk about that, what are the basic design parameters? So, there are few design parameters, or primarily 3 design parameters, which are frequently used for parametric study for axial compressor. One is the flow coefficient, so which is represented usually phi. So, one can write that it will V z by u. So, this is a ratio between axial and the rotational speed. Second could be stage loading. So, that is typically represented at psi. So, this is the ratio of delta H naught by u square, which is delta V theta by u. So, enthalpy rise, that is the ratio of total enthalpy rise to the blade kinetic energy. And third could be degree of reaction, which is like this. Now, that so this is given as a ratio of Cp delta T r by Cp delta T T, which is a ratio of static pressure, rather static enthalpy rise in rotor divided by static enthalpy rise in stator in whole stage. Okay. So, this is where the, if you look at that diffusion pressure or the pressure rise, that takes place both in stator and rotor, and but it increases in static, I mean that essentially increases the static pressure. So, the total pressure rise could be attributed to the both the blade rows. Rotor does the dynamic work, hence pressure rise in the rotor is an important design factor, because this does the dynamic, they exposed to the dynamic loading, and that is why the degree of reaction is sort of represented like this. Now, if Cp is assumed to be constant, then psi become, essentially we can write it is then static temperature rise in rotor to static temperature rise in whole stage. Okay. So, if you consider a blade state, so this how the velocity triangle would look like. So, that is u, beta 1, alpha 1, V 1, W 1, and so these are my blade rows. So, that is let us say a rotor, then there would be the velocity triangle. So, this is again W 2, beta 2, u, alpha 2, B 2, then there is a set of so finally it goes out like this. So, this is you can think about a blade state like that you have rotor and stator, and that now we can derive the expression for degree of reaction. So, let us assume that V 3 would be equals to V 1. That means, air leaves the stage with same axial velocity with which enters. So, that gives you back the delta T stage would be delta T overall stage. So, I can write T naught 1 is T 1 plus V 1 square by 2 C p, and T naught 3 is T 3 plus V 3 square by 2 C p. Second, V z is constant throughout the stage. So, that gets me back T naught 3 minus T naught 1 would be delta T overall stage. So, T 3 C p minus V 1 square by C p. So, that gives me T 3 minus T 1, which is delta T stage. So, which one can write? So, change in static temperature, change in the stagnation temperature of the stage. So, this is change in static temperature, which is the change in stagnation temperature. Let delta T r is assumed to be static temperature rise in rotor, and delta T s is static temperature rise in stator. So, just careful with the subscript, because when I use S, that is stator, but when I use ST, that means the whole stage which is represented. Now, we use the energy equation of the stage. So, W equals to C p delta static, which is C p delta T r plus delta T s. Now, what we have seen that u delta V theta, which is u V theta 2 minus V theta 1. So, since u 2 is u 1. Okay. Now, one can write that V theta 2 is u 2 minus W theta 2. So, this would be u 2 minus V z tan beta 2, and V theta 1 is u 1 minus W theta 1, which would be u 1 minus V z tan beta 1. But u 2 is u 1. So, that gives me delta V theta is V z tan beta 2 minus tan beta 1. So, similarly, it can be shown that delta V theta is V z tan alpha 2 minus tan alpha 1. So, using the velocity triangle, one can also show this is there. So, what is delta T r plus delta T s? So, this is u V z tan beta 1 minus tan beta 2, or u v z tan alpha 2 minus tan alpha 1. But all the work is done by the rotor. So, all the work is done by the rotor. So, steady state steady flow analysis yields that W equals to C p delta T r plus half V 2 square minus V 1 square, which is delta H O r. So, one can show that like 2 u by V z would be tan alpha 1 plus tan alpha 2 tan beta 1 plus tan beta 2. So, this can be shown. So, that is what we can use this and write C p delta T r plus half V 2 square minus V 1 square equals to u V z tan alpha 2 minus tan alpha 1. So, C p delta T r equals to u V z tan alpha 2 minus tan alpha 1 half V 2 square minus V 1 square. It is just an rearrangement of the thing. Now, we can replace V z is V z sec alpha 2 and V 1 equals to V z sec alpha 1. So, this would be V 2. So, that gets me back C p delta T r equals to u V z tan alpha 2 minus tan alpha 1 minus half V z square sec square alpha 2 minus sec square alpha 1. So, further simplifications it will get us tan alpha 2 minus tan alpha 1. So, minus half V z square tan square alpha 2 minus tan square alpha 1. So, that is the using the trigonometric relation that sec square alpha is 1 plus tan square alpha. Now, the definition says degree of reaction is C p delta T r divided by T r plus T s C p. So, if I replace this back u V z tan alpha 2 minus alpha 1 minus half V z square tan square alpha 2 minus tan square alpha 1. So, which will get me so this will be 1 minus half V z by u tan alpha 2 plus tan alpha 1. So, this is what one would get. So, similarly, one can show that this would be V z by 2 u tan beta 1 plus tan beta 2. So, that is also possibly can be seen or done. So, if you consider a special case where let us say 50% enthalpy rise in rotor and 50% in the stator, then this would be 0.5. So, which means half equals to V z by 2 u beta 1 plus tan beta 2, which gives me back tan beta 1 plus tan beta 2 is u by V z. Okay. So, now going back to the velocity triangle. So, if you go back to the velocity triangle, this is how it looks. So, this is W, this is beta, this is alpha, V, this is U. So, this portion is W theta, this portion is V theta. So, what we get V theta by V z is tan alpha. So, that means V theta equals to V z tan alpha, and similarly W theta is V z tan beta. So, V theta plus W theta, which is u, one can get V z tan alpha plus tan beta. So, from where one can write u by V z is tan alpha plus tan beta. So, either one can write like tan alpha 1 plus tan beta 1, which is tan alpha 2 plus tan beta 2. So, for 50% or 0.5 degree of reaction, we get u by V z tan alpha 1 plus tan beta 1 equals to tan alpha 1 plus so we can write tan alpha 1 plus beta 1 equals to tan beta 1 plus tan beta 2, which we have got here, tan beta 1 plus beta 2. So, if we put that, this gives me back that alpha 1 equals to beta 2. Similarly, I can write tan alpha 2 plus tan beta 2 equals to tan beta 1 plus tan beta 2, which will provide me alpha 2 equals to beta 1. So, these are the conditions when you have 50% of the degree of reaction. So, V z is constant throughout the stage. So, since that is there, so one can write V z equals to V 1 cos alpha 1 equals to V 3 cos alpha 3 and V 1 equals to V 3. So, which will get alpha 1 equals to alpha 3. So, that means alpha 1 equals to beta 2 equals to alpha 3 and beta 1 equals to alpha 2. So, this kind of design, when we get these angles like this, so these are called this kind of design called symmetrical blading. Okay. So, the blade design will look like that. So, if you look at the different scenario, then this is how it is going to look like. Let us say we have this. So, this okay. So, this is u, this is V 1, this is W 1. So, this is W 2, and this component is V2. So, this is where this is the case where is 0% and beta 2 is minus beta 1. So, this is my beta 2, this is going to be my alpha 2, this is alpha 1, this is beta 1. So, that is the situation where this is the case. Now, when this is 50%, that is the case alpha 1 equals to beta 2 and alpha 2 equals to beta 1. So, my profile will look like different. So, this will go like that. So, that is my V1, W1. So, that is W2, this is B2, alpha 1, beta 1, alpha 2, beta 2. Okay. So, and the last situation which could possibly happen is that like this, and I can have this, this is U, so this is W2, beta 2, alpha 2, V2, W1, V1. So, this one alpha 1, this one beta 1, and this is the case where psi is 100%. So, alpha 1 is minus alpha 2. So, these are different velocity triangles for different degrees of reaction. So, we will continue the discussion in the next lecture.